Hi, it's Ryan. This video is going to continue on our discussion about fundamental quantities. We were discussing fundamental units in the last one. This one will discuss fundamental measures of motion. So we're moving along. Fundamental measures of motion pertain to things like displacement, distance, velocity, acceleration, things like that, and we'll go through them. And so our fundamental measures of motion will begin with something called displacement. Displacement. Displacement is a change in position and we could make a note here too. So it's a change in position. We could note it's the straight line distance, or we could say it's the straight, I like that, the straight line distance that is measured between the final and initial points. Now, I actually want to adjust this. I don't want to say distance. I'm going to actually X that out in red. It's the straight line, and we could let's just say measurement, because displacement and distance are different. Displacement is something we would like to call a vector quantity. Displacement is a vector quantity. Since this is really our first time ever saying that word as a class, I would like to make a brief note on that, and we will do a whole video on vector review for you in case you're rusty. But in general, so let's just make a little note. Let's do our note in this light blue. So we'll say note. In physics, and really in the world, but in physics, we have two types of numbers. And arguably there are more. There are like imaginary numbers and other things. So this is true, but this isn't really encompassing all of physics. But anyway, in physics, we have two types of numbers. The first are vector quantities. I shouldn't have said numbers. I should have said quantities. Two types of quantities. The first are vector quantities, and the second are scalar quantities. Scalar or vector quantities are quantities with both amount or magnitude, so I'll write this, quantities with both magnitude. Magnitude is the math word for amount, with magnitude and direction. Scalar quantities are just numbers without direction, or quantities without regard for any direction. So quantities with only amount, no direction. So anytime we have a number that we have to talk about both the amount or the magnitude and the direction, then we'll be talking about something that is a vector quantity. And displacement happens to be a vector quantity. Well, as we do this, I like to always show you diagrammatically the definitions. But first off, we've defined displacement. We've told you it's a vector quantity. Now we can tell you the symbol for displacement. The symbol for displacement, I like to use an S. And anytime we have a vector, we put a vector symbol above it. And so that's like a little arrow with half a head. And they always point the same direction. It doesn't matter if what way our vector is actually pointing. This is just a vector symbol. This just indicates that S is a vector. Now I don't use D for displacement, and we'll see why soon, but I like to use S. So our symbol is S with a vector symbol. Our unit, of course, will be the meter. And so now I can show you diagrammatically what I'm talking about. So if we have something that moves from some initial position to some final position, there's kind of a number line. This would be our initial position, xi. Let's actually say si, sorry. And maybe this will mark our final position, sf. Then our displacement vector will look like so. We'll just create an arrow that points in the direction of the final position. This is S. So vectors are created by literally drawing arrows. We also could show mathematically. Mathematically, we know that the change in displacement, or the change in position, as we defined for you, a change in position. Well, our final position is SF and our initial position is SI. So our change in position, we always use the same symbol. So S is given by the change in position. And we'll say, in this case, it's in the horizontal direction. We always want to give the direction as well as the amount. Well, this is a Greek letter, delta. And anytime we have delta, what delta means is we have to take final minus initial. So S vector is really equal to the final position minus the initial position, and we would say horizontal. You could also say at 0 degrees if you'd like, but we'll talk more about vectors another time. So the thing to really remember is that anytime you have a delta, delta means change in. And anytime we say the change in, we always want to do final minus initial. So that's something you kind of want to bury into your minds. But that is a pretty decent layout of the diagrammatic and mathematical definition for displacement, which is a vector quantity. And it's always the straight line arrow like so between the final and initial position. Our next quantity is called I just did displacement. It's called distance. I think we were doing purple for that. So now we have distance. Distance is really just what it sounds like. It's a quantity you're more used to working with. Distance is a scalar quantity. That's how we should start it. A scalar quantity. That means distance doesn't care about direction. It's a scalar quantity. The symbol we'll use for distance is a lowercase d. The unit will, of course, be the meter. We're not going to give you a mathematical definition right off the bat for distance, but let's show you diagrammatically first. Maybe we can come up with a mathematical definition. So diagrammatically, and what I'm going to do to show this is I'm going to draw just three pictures, let's say. So one will look like this, where this is our initial position and this is our final position. The next will look like this, where this is our initial position and this is our final position. And our last one will look like this. So this is both our initial and our final position. And so we're going to imagine that someone might be walking along these paths. And what I'd like us to do is determine what the distance and the displacement for each of these paths are. And in order to do that, I'm going to have to give you a little more information. We know that these are a in length. We know that this could have radius of a. And we know that these are a in length as well. So now I'd like to get both the distance and the displacement, but in order to do the displacement, what I'd like to do is just show the displacement vector, which I used that blue for, so I'll use that blue again. So let's go ahead and write in both the distance, d equals, and we'll show the displacement vector as well. So for this first one, what do you think? What distance would we travel if we start here and we walk a, and then a again back down to here? Well, wouldn't distance just be a plus a, or 2a? Well, of course. What would our displacement vector look like? Well, we start here and we end here, and we have to do the straight line shot from the initial to the final position. And so it's clear that in this case, s, the magnitude of s, is less than the distance that we would travel. And you can see why displacement and distance end up being different often, or many times. How about this one? What would it take to start here and walk along this perfectly circular path to here? Do you remember the circumference of a circle? Isn't it 2 pi r? And r in this case is a, 2 pi a. But a circle is all the way around, and so we know that this isn't a circle, it's a half of a circle. So we would divide that by 2. So we know the distance in this case is pi r, but pi a because r is a. And the displacement vector would go like so. The displacement then would be just 2a, wouldn't it? S would be 2a, but it would be horizontal, or in the x direction if you want. Horizontal, because we know displacement is a vector. We have to give the direction too. Finally, what is distance for this shape? Well, of course, we're walking a, all the way around, so we have 4a. What is the displacement? We'd have to do a vector from here to here. Wait a minute. So wouldn't the position, the final position, and the initial position be the same? And if we did final minus initial, that would be 0, wouldn't it? So our displacement in this case is 0. Even though we have a 4a distance, final minus initial yields a 0 displacement. So there are some tricky questions you could be asked where really your displacement is simply 0, even though you moved all over the place. And that's why we don't really have just a single mathematical definition for distance. Well, if we were a calculus class, we would just show you the arc length integration equation, but we're not, and so we don't really have any clear-cut distance equation, but as long as you make a nice picture, you'd be able to figure out the distance if you were ever asked. So distance was our next fundamental quantity of motion. And that means we've had a displacement, which is a vector, and a distance, which is a scalar. We'll kind of stick to this pattern where we'll have scalars or vectors, depending on what we're talking about. Our next quantity that we need to discuss is velocity. Velocity is a vector quantity. So velocity is another one where you have to always mention both amount or magnitude and direction. The symbol I use for velocity is a V with serifs. So the symbol looks like this. And the reason I use those little curly V's like that is mostly for physics 2 when we start to talk about voltage, but I like to use the V like that. In general, I'll give you the unit. The unit is the meter per second. We always measure in meter per second. In general, velocity, I guess I should have defined it first. Velocity is the rate of change of displacement. Oh, I don't like that. I'm sorry. We have to make that simpler. Let's redo that. Velocity is the change in displacement with respect to time. The change in displacement with respect to time. Mathematically, what we will be using in our class is the equation for the average velocity. So we'll say the average velocity, V average, is equal to the change in displacement over the change in time. And of course, those deltas always can be changed to final minus initial. In case you're curious, there is a V instantaneous equation, and V instantaneous is given by really a derivative, but it's the limit as delta t goes to 0 of the change in displacement with respect to time. And so that would give us our instantaneous velocity. This is really just ds dt, and that's calculus, and so we don't use it. But in case you were curious, what we use is V average, which is change in displacement over change in time. Normally I don't do this, but I think since we're online, we won't have as much opportunity to talk. So I would like to show you diagrammatically how we can represent a velocity. Diagrammatically, we could plot a displacement and a time, or a displacement with respect to time. And so let's just imagine you're watching somebody drive along on a highway. If somebody's driving along on a highway, maybe going a constant 70 miles per hour, and you start the clock somewhere over here, so at 0, they're somewhere on the displacement line, and every second that goes by, how far would they go? Well, you could figure that out if you wanted, but we know they would go up by a certain number of miles, and so every second that goes by, we could label their position. This would be called a position versus time plot. Note that I always write y versus x. It's never x versus y, and that'll be very common, especially in your labs. And then once you have all the data on your plot, you can create a line that goes through those points. And so that line would represent a change in position with respect to time. Well, with respect to just means that our x-axis is the time. So this graph represents a change in position. Now notice our velocity is just the change in position divided by the change in time, but isn't that just taking the rise over the run? Does that ring any mathematical bells for you? The rise over the run. Well, isn't that just the slope of our line is rise over run? And so that would really be the change in s over the change in time, but that's just the velocity, isn't it? So you can plot the way that things change position with respect to the time, and you would be showing with the slope of that line the velocity. The next quantity we may discuss, or we have to discuss, is speed. Speed. Speed is a scalar quantity. And it's a scalar quantity defined as the change in distance with respect to time. And so we could just show you quickly now that, of course, our unit would be the meter per second still. And our symbol, this one's kind of weird. If you use a different symbol, I mean, you can always use different symbols as long as I know what you mean, as long as you define them for me. But the symbol I use is a V with an S because it's a speed. Mathematically speaking, it would just be the delta D over delta T. And again, that's the average speed. Finally, the last of our 5 fundamental measures of motion that we're discussing is acceleration. And acceleration is so important, and so many students confuse it or make it more than it needs to be. In general, acceleration is a vector quantity, so we need direction. It's a vector quantity. The symbol, I'll define it. So it's the change in velocity with respect to time. The change in velocity with respect to time. Our symbol will be an A, but of course with a vector symbol. If it's the change in velocity with respect to time, what will the unit be? We're taking a change in meter per second and dividing by seconds, so what do we get? Well, a meter per second, of course, but we always shorthand it to say meter per second squared. Have you ever heard anyone on some science show say meter per second and thought, wow, that sounds nerdy? It actually makes some sense. If we write this as a meter per second, what we're saying is the change in velocity, there's a delta V, that's 1 meter per second, and that happens every second. So mathematically, we know that that will be A equals the change in V over the change in t. And don't forget your velocity is a vector, and it gets a vector symbol. So those are our 5 fundamental measures of motion that we need. We know then, and we could just note, this is our average for instantaneous. We know we would use dv dt, but again, that's not for our class, and so I just like to make sure you've seen it. So those are our 5 fundamental measures of motion. So diagrammatically, we forgot to do diagram, so we could say diagrammatically, we could plot a velocity versus time plot. And so we'll have v in meters per second and t in seconds. And now if you have someone maybe stopped at a stop sign where t equals 0 and they accelerate up to maybe 30 miles an hour or something, well, in meters per second, that's gonna be approximately like divide by 2, take off 10%. That's the trick. So if you divide the 30 by 2, 15, take off 10%. So you're looking at roughly 13.5 meters per second. And so maybe it would go every second up a little bit. And if we change our velocity at a constant rate, then the change in velocity over the change in time would yield the slope of our line, and the slope would be delta v over delta t, and that would be a. So we will have you plotting in your lab in particular.